Okay, hi everybody. It's very nearly the last thing in advanced higher then. This is capacitors and inductors. And why are these in the electromagnetism unit? Well, these are two electronic components that use the properties of electric fields and magnetic fields for their operation. So firstly then, capacitors. Now you did capacitors in higher physics, or at least I hope you did, but we need to do a little bit of revision of them first. So what is a capacitor? Well, there's a wee diagram of one there at the bottom. It's basically two metal plates separated by an insulator. That insulator is called a dielectric material, but it's just an insulator. It's maybe paper or wax or some insulating material so that the metal plates don't touch each other. Now, capacitors store charge and capacitors store energy. It's a bit like a jug in a way, you know, a jug stores water. Well, a capacitor stores charge, but unlike a jug that's got a fixed capacity, the amount of charge that a capacitor can store depends on the voltage that you put across it. And in fact, capacitance is defined as being the amount of charge that a capacitor can hold for every volt that you place across it. And capacitance is measured in a unit called farads, after Michael Faraday. But 1 farad just means that a capacitor can store 1 coulomb for every volt that you put across it. So if you place 1 volt across the capacitor, it will store 1 coulomb of charge. A 1 farad capacitor, by the way, is a very big capacitor, giant big capacitor. Now, there was 2 relationships on your relationship sheet involving capacitance last year. C equals Q over V. Capacitance is the amount of charge stored per volt, and the energy stored on a capacitor is half the charge times the voltage across it. Both of them still on your relationship sheet. Now, you may or may not have seen the demo last year that allows us to determine the relationship between charge and voltage on a capacitor, but it won't do any harm to go back and have another look at that. This is a demo that we would do with a higher physics class. Okay, troops, this is a wee quick experiment to determine the relationship between the voltage across a capacitor and the charge stored on that capacitor. So, here's the plan. We're going to try and determine the relationship between the charge and the voltage on a capacitor, and from that relationship determine the capacitance of the capacitor. And there's our little circuit that we're going to use. 4 cells connected to a capacitor, the voltmeter across the capacitor, a little 2-way switch, there's a wee 2-way switch here, and then a coulometer on the far side. There's the apparatus. There's our 4 cells. There's our capacitor. It's a 0.047 microfarad capacitor. More about that later. And there's our little 2-way switch. And there's the coulometer. And what the 2-way switch allows us to do is, if I move the switch to the right, then we'll measure charge on the coulometer. I'm going to reset that just now. It's reading 0. If I move the switch to the left, then the capacitor will charge up. By moving the switch to the left, we're on the charging side of the circuit. When I move the switch to the right, we dump the charge from the capacitor onto the coulometer, and the coulometer measures the charge that was stored on the capacitor. Now, we are going to move the switch to position A, but just with 1 cell, measure the voltage across the capacitor when it's fully charged, then move the switch to position B and measure the charge stored on the capacitor with the coulometer, and then repeat that with 2, 3 and 4 cells. So we're going to start off with 1 cell. So I just want 1 cell here, and we want to make sure that that coulometer is empty, and we're going to measure the voltage across the capacitor when it's fully charged. So plug my voltmeter in. There's my voltmeter here. And just with 1 cell, we're reading 1.48 volts. So I'm going to put that on my table. We've got 1.48 volts from 1 cell. Then that 1.48 volts, I'm going to disconnect my voltmeter first. And then I'm going to move the switch over to the right hand side, make sure that's reading 0 to start with. Ready? I'm going to dump all that charge over. And it's reading 69 nanocoulombs. Let's put that on the table. I'm going to reset that again. And we're going to move our switch back over, but this time using 2 cells. So with 2 cells this time, move the switch back over. Let's measure the voltage across. Let's measure the voltage across the capacitor with 2 cells. It's 2.97. Okay. 2.97. And then we'll move the switch over and we will measure the charge stored on the capacitor with 2 cells. Take my voltmeter out again. Ready to dump it across. And it's 141 nanocoulombs. Same again, but this time with 3 cells. So 3 cells, we've got a voltage of 4.33 volts across the capacitor. So 4.33. And when we disconnect that and then dump the charge across, we get 205 nanocoulombs. Last one then, all 4 cells across the capacitor, we're getting a voltage 5.83 volts. Put that on my table. Disconnect the voltmeter. The reason I'm disconnecting the voltmeter is so it doesn't leak. The capacitor doesn't leak through the voltmeter. When I switch the switch over to the other side, the capacitor's just going to empty out onto the coulometer. So here's my last one. Switch it over. 276 nanocoulombs. There's all my results then on the table. We're going to draw a graph of charge against the voltage, and then hopefully from the gradient of that graph we're going to see the relationship between the charge stored on the capacitor and the voltage across it. And bear in mind our capacitor was 0.047 microfarads. I want to bear that in mind when we draw our graph. There's our wee capacitor there, 0.047 microfarads. Let's see what happens when we draw the graph. See you in a bit. Now what's good about that graph is it was very quick to do. We can see it's a linear relationship. There's a slight y-intercept. There's a y-intercept of -1. And that tells us there's a systematic uncertainty in either the charge reading or the voltmeter reading. But more importantly, the gradient is 48. 48, now it's nanocoulombs over volts. 48 nanocoulombs per volt. And the definition of the capacitance of a capacitor is how much charge it can store per volt. So in this case, it's 48 nanocoulombs per volt. So it has a capacitance of 48 nanofarads. And 48 nanofarads is the same as 0.048 microfarads. And what did ours say? What was stamped on the capacitor? 0.047 microfarads. We were out by 1 microfarad. That's about 2%. That's not bad. But anyway, there you go. That's a little demo of how to determine the relationship between the charge and the voltage across a capacitor, and from that graph to determine the capacitance of the capacitor. Now, capacitors take time to charge up, and the time that they take to charge up depends on the size of the capacitor and the resistance of the charging circuit. If you want to think about it a wee bit like a tap and a jug, the amount of time it takes for a jug of water to fill up depends on the size of the jug and the speed of the water that's flowing out of the tap. And you control that speed of the water by adjusting the tap. The tap is like the resistance to the flow of water. Well, a resistor is the resistance to the flow of charge in a charging circuit. So, bigger capacitor, bigger resistance, longer charging times. And there's the sort of graphs that you may have seen before. If not, I'm going to show you another wee video on charging and discharging of capacitors for the voltage anyway, and let you have a wee look at that. Okay, we've got a wee quick video this morning just because I tried this with my higher class and nothing would work. So now we've got it working. Hopefully going to be able to show you this in 30 seconds or so. This is graphs of charging and discharging a capacitor, graphs of the voltage across the capacitor and the current. Okay, let's have a wee look. So we've got a battery. Battery is connected via a variable resistor and an ammeter to a capacitor. Okay, that's the charging side of the circuit. And then through a two-way switch, we can move the switch to the right, and that same capacitor will discharge through the ammeter through this second variable resistor. And the CRO is there to monitor the voltage across the capacitor. So first things first, I'm going to discharge it. Just empty it out. So move the switch to the right. The capacitor's empty, so my spot on my CRO is at the bottom of the screen. That's representing 0 volts. Now, as I charge up the capacitor, it's a 1000 microfarad capacitor. As I charge it up through this variable resistor, a 1 kilo ohm variable resistor, let's watch what happens to the trace on the screen. So I'm ready to charge it up, and there we go. I'm now going to empty it out by switching across to the right hand side. Watch the trace. I'm going to show charging and discharging. These are the voltage graphs. Charging, discharging. Again. Okay. What about the current? What happens to the current when it's charging? Watch this little ammeter here. Here's the current when it's charging. Maximum falls to 0. And then when it's discharging, have a guess? Watch, this is it discharging. So when it's charging, the current is instantly at a maximum, and then it gradually falls to 0. Watch. And then when the capacitor discharges, the current flows in the opposite direction. Off the capacitor, falls to 0 again. That's charging and discharging of a capacitor. Oh, other thing. If we want to change the rate at which it charges up, we just need to alter the resistance. Or if we want to alter the rate at which it discharges, we just need to alter the resistance. Bigger values of C and R mean longer charge times. Smaller values of C and R, shorter charge times. There you go. Have a great day now. Now, a circuit with a resistor and a capacitor in it has what's called a time constant. The time constant of the RC circuit. R and C stand for resistor and capacitor. Now, the symbol for the time constant of an RC circuit is that symbol tau, Greek letter there. Tau, kind of T with a kind of curly bit at the bottom. We've used that symbol before. I think we used tau for torque earlier on in the course. So, there's a little circuit there, very similar to the one I showed you in the video with the charging circuit when you move the switch to position P, and it discharges through the bulb when you move the switch to position Q. I suppose the question is then, how long does that capacitor take to charge up to 12 volts, which is the supply voltage? Well, the way that you work out the time constant of an RC circuit, and by the way, this is not the time that it takes to fully charge. The time constant is the product of the resistance and the capacitance in the charging side of that circuit there. So if we've got a 56 ohm resistor and a 150 millifarad capacitor, if you multiply those two numbers together, you get what's called the time constant of the circuit. And the time constant gives you the time it takes for the capacitor to charge to 63%. And I know what you're going to say. You're going to say, why 63%? We'll get to that. So there's our little relationship. The time constant of an RC circuit is the product of the resistance times the capacitance. So in this circuit, the time constant would be 56 ohms times 150 times 10 to the minus 3 farads is 8.4 seconds. So that means it takes 8.4 seconds for that capacitor to charge to 63% of its full charge. And a capacitor is said to be fully charged or discharged after 5 time constants. So in this case, the capacitor is fully charged after 42 seconds. Now the reason for the 63% arises from the mathematics of continuous growth and decay curves. And more detail of this is given on the next slide, but it's not examinable. Now if you want to skip past this bit, then feel free, because we're going to be using a bit of maths here that you may or may not have covered. We're going to be using Euler's number. It's the letter E. There's an E button on your calculator. It's a number that's approximately 2.71, and we need that number for continual growth and decay curves. And for the charging and discharging of capacitors, that's what these are. These are exponential growth and decay curves. And the voltage across a charging capacitor at any time is given by this relationship. So VC is the voltage across the capacitor at any time t, and it's equal to the supply voltage times 1 minus e to the power of minus t over RC. Now E is Euler's number, otherwise known as the base of the natural logarithm. When t equals RC, if we substitute in RC into that relationship, for t, we get RC over RC, which is 1. And then if you do that on your calculator, if you do 1 minus e to the power of minus 1, you will get 0.63. So the voltage across a capacitor will be 0.63 times the supply voltage after 1 time constant. So after 1 time constant, it's 63% charged. After 5 time constants, if you want to substitute in 1 minus e to the power of minus 5, you'll get 99% charged, and so on. Now remember, this is not in the course. This relationship is not in the course. The base of the natural logarithm is not in the course. All you are required to know is that if you multiply the resistance times the capacitance, you get a number that is called the time constant of the circuit. Now you might be thinking, hold on, if we multiply a resistance times a capacitance, how do we get a time? Well, let's think about the units here. R equals V over I, that's Ohm's law. And our definition of capacitance, C equals Q over V, it's the amount of charge it can hold per volt. Let's think about the units of them and then we'll multiply them together. So R times C is V over I times Q over V. Our two V's will cancel out and we're left with Q over I. And if you remember from your 3rd year physics, Q equals I times T. So Q over I equals T. So if you multiply the resistance times the capacitance, you get a quantity that has the same units as time. Now there's very little then you can get asked about capacitors in an advanced higher paper, because you won't be asked about anything that involves the mathematics of exponential curves. So you can only be asked about the time constant relationship, tau equals R times C. So let's have a little look at a past paper question, and it's usually quite easy marks to get. So this was from the 2017 paper. A student purchases a capacitor with a capacitance of 1 farad. That's a big capacitor. The capacitor has negligible resistance and is used to supply short bursts of energy to the audio system in a car when there's a high energy demand on the battery. That's if you're playing your tunes dead loud. So the instructions state that the capacitor must be fully charged from a 12 volt DC car battery through a 1 kilo ohm series resistor. And we've to show that the time constant for this charging circuit is 1 times 10 to the 3 seconds. It's a show question, so we have to show our relationship, our working, and get that answer. Now the only relationship we have is tau equals RC, and we're told that it's a 1 kilo ohm resistor and a 1 farad capacitor. Now make sure you put the numbers in exactly as they are in the question. It's a show question, and that means that our time constant is 1.0 times 10 to the 3 seconds as required. It's about the easiest 2 marks you'll get in the paper. But we're not finished. It says the student carries out an experiment to monitor the voltage across the capacitor while it's being charged. Draw a diagram of the circuit which would enable the student to carry out this experiment. Very difficult. Very few people were able to do this right. So it's a 12 volt battery. A single cell symbol would be okay. We need our capacitor, and it's charging up through a series resistor there. Now, we don't need to label them, we just need to draw the diagram, and we're monitoring the voltage across the capacitor. That's it for 1 mark, but very poorly done. Okay, let's move on. Then we've got a graph, and it says using the information from the graph, show that the capacitor is 63% charged after 1 time constant. There's that 63%. Now when it's fully charged, then it'll be 12 volts. So after 1 time constant, what will be the voltage across the capacitor? Well, we know what the time constant is. We've just worked it out. It was 1,000 seconds. So if we read the graph at 1,000 seconds, the voltage across the capacitor is, now let's have a look at that graph. It looks like each wee box is 0.4, so that will be 7.6 volts at 1,000 seconds. And if we work out what 63% of 12 volts is, because 12 volts is the maximum voltage, 63% of 12 volts is 7.6 volts. So at 1,000 seconds, it is 63% charged. Next bit says using information from the graph, determine how many time constants are required for the capacitor to be fully charged. Well, it's fully charged at 12 volts at round about that point there, which is at 5,000 seconds. And since we know that the time constant for the circuit is 1,000 seconds, then that means that there were 5 time constants. The capacitor will be fully charged at 5 time constants. Now the last part of this question is your worst nightmare. It's an open-ended question. It says use your knowledge of physics to comment on the suitability of the capacitor as the only energy source for the audio system in the car. And the car audio system is rated at 12 volts and 20 watts. Open-ended questions are good if you're given numbers. Use those numbers. We're told that the power is 20 watts, and we're told that the voltage is 12 volts. So we could work out current, but it's really a question about capacitance. So we could work out charge as well. Remember from your relationship sheet, capacitance C equals Q over V. Well, that means that Q equals CV. So the total charge that could be stored on this capacitor would only be 12 coulombs. Now we could work out the average current that would be flowing, because I equals P over V, which would be our 20 watts divided by 12 volts. And that would give us an average current of 1.7 amps. And if we know the average current and the charge stored on the capacitor, we could work out how many seconds this would last for. T equals Q over I, 12 over 1.7 is about 7 seconds. So this capacitor could only supply charge to the car audio system for about 7 seconds. And that's just one way that you could answer this question. There are a whole number of other ways and a whole number of other things you could include. You could include the fact that in a capacitor, as soon as it starts discharging, then the voltage will drop. So you won't get a constant 12 volts from the capacitor. It drops as soon as it starts supplying energy to the car audio system. And there's a whole number of other things you could have talked about. Open-ended questions are what they are. They're open-ended. You could write whatever you like, any kind of similar answer. But good advice is include relationships, include calculations to help you construct a good, full answer. Okay, see you in the next one.